Okay, so here's one. We want to draw the shear force and bending moment diagram for this. Let's just assume, for the sake of argument right now, that you didn't know anything about drawing shear moment diagrams in this approximate mode, and you were stuck with writing equations for shear force and bending moment and then plotting them. Could I write one set of equations for shear force and bending moment for this diagram? No. How many would I have to write? I have to write one from 0 to 1, a second one from 1 to 2, a third one from 2 to 6, a fourth one from 6 to 7, and a fifth one from 7 to 8. You'd have to write 5 sets of equations. Why? Because of the discontinuous in the loading, right? That would take you a better part of an hour probably to pull off, I would guess. We're going to do it in about 10 minutes and still be able to pick off the high points, maximum moment, maximum shear by using this approximate method. So this is an extreme example, but it does show that there are times when this approximate method is going to be superior to writing the equations. Now to get started, I'm going to need to know shear force and bending moment if I can at beginning and end. Let's talk about moment first. What's the moment here at the left edge? Yeah, it's 0. What about at this pin?
0.
Also 0. But I need to find the shear force values. So I'll come over here and draw a free body diagram. And I will assume positive shear. Let me call that A and B. So there's positive shear at A. There's positive shear at B. And I've got this load right here. Let's see, that's 8 kilonewtons. And there's one over here. That's 4 kilonewtons. And then I'm going to turn this distributed load into a concentrated equivalent to help me manage that. And it's rectangular shaped, so the area of a rectangle is just base times height. In this case, 4 meters times 4 kilonewtons per meter. So that's going to be 16 kilonewtons. And the centroid is going to be right in the middle at 2. So this is going to be a meter. And then a meter plus 2 is going to be 3. And then 2 plus a meter is 3. And then 1 more meter. I think that's got all the dimensions. So we just need to find the shear forces. So I'm going to start by summing moments at one point. You guys have a point you want to do it, A or B? Does it matter? Somebody pick.
A, B.
A, B. I don't know the point. We'll just do B. Why not? We'll just do B. That's a change. So we could do A. Doesn't matter. Let's sum moments at B. So when I do that, I'm going to use right-hand rule. So summing moments at B, all these forces create what kind of moment about B? Positive or negative? Positive. So 1, 2, 3, 4 forces. We'll start with this one. So positive 4 kilonewtons with a moment arm of 1 plus 16 kilonewtons with a moment arm of 4 plus 8 kilonewtons with a moment arm of 1 plus 3 is 7. And then the reaction, the shear force at A, what kind of moment does that create about B? Positive or negative? Negative. And the moment will be the shear at A times its moment arm, which is its total distance, which is 8. So what is the shear at A? $15.5. I'm guessing. Is that what it is? Mr. Van Tilburg, how you want to come in and work some problems with us?
Mm-hmm.
No?
I'm learning about bearing and tear out right now.
Oh, nice. I forgot what I said. What did I say? 15 point? 15 and a half?
He's always right when he has his tips.
That's not true. Ask my wife.
Like 75%.
It came out positive, so the shear at A is positive. So how do we find the shear at B? You could sum moments at A if you like, but I think I'm going to go a easier route and just sum my forces in the y direction. I'm going to assume up is positive. So starting at A, it's up. B is down. That's negative. And all my forces are down. So that's minus 8 kilonewtons, minus 16 kilonewtons, minus 4 kilonewtons. So what is the shear at B? I think it's going to be negative 12.5? You guys get 12.5?
Yes.
I believe this class, in all my years of teaching since 1993, might be the quietest class I've ever had. I mean, you guys, I could hear a pin drop in here. Are you guys here today? You're like this every day, though. It's not unusual, is it? You're just a quiet group. Why is that? You're very contemplative and thoughtful and considering all options, very cerebral? Yes? I would say yes to all those things, right? Bored? Would that be part of it? No? Okay. All right, so we got our shears. Let's go and build this diagram. So I'm going to start with where I'm going to begin and where I'm going to end. Are there some other points that might be important along the way? Well, every time you see a point load, you know that's a pretty important point. Because as we go from left to right and go past that, we know our shear diagram is going to jump. So let's add those to our template. And then also we've got nothing going on here, but then we jump up and do have a continuous load and then change. So probably the beginning of that distributed load and the end would be another possible place where we might want to look at things. So let's start with that. We might modify that some later. And let's assume we have a positive X, a positive shear, and all of our units in this problem will be in kilonewtons. So let's put on there what we know about shear. What's the shear at A? And we solved for that, right? It was 15.5 positive. And we also solved for the shear at B, which was negative 12.5. So we've got a starting point. We've got an ending point. Let's see if we can make those two things connect. And remember, our relationships are that the change in shear between any 2 points is area under the corresponding part of the load diagram. And then, of course, the slope of the shear diagram, given by the derivative, is equal to the load at every point. So let's look at this first little 1 meter segment. If I go up here and look at the area under the load curve, what is it? Well, the load is 0. So the area of that is 0. So there is no change in shear. So my shear should stay at 15.5. What kind of curve should connect those 2 points? Well, according to my relationship, it should be a slope given by the load. And what's the value of the load everywhere in the first meter? 0. So 0 slope is horizontal line. So it looks like we've got a constant value for the shear over the first meter. Now, as I go from the left side to the right side and we pass under this applied load, how much is my shear change? 8 kilonewtons. Is that positive or negative change? Negative. So what's 15.5 minus 8? 7.5. So it drops down to there. Now what's the change in shear over the next 1 meter segment? You go up and look at the area, and what's the area of the load curve? 0. So no change. It stays 7.5. And what's the slope of this curve? Well, according to this, the slope of the curve is given by the load. And what's the value of the load there? 0. 0 slope, horizontal line. So my shear diagram just kind of steps down a little bit. Now, what's the change in shear from 2 meters to 6 meters? This segment. If I go up and look at the area under the load curve there, what do I have? Well, it's a rectangle. Base times height. So the base is 4, the height is 4 kilonewtons per meter. So that's 16. Is that a positive or negative area? Negative. So what's 7.5 minus 16? What is it? 8. 8.5, right? I don't have this to scale, so let me do the best I can. So this should be negative 8.5. What's the slope of the shear diagram? Well, it's the load. Well, let's look at what the load is. So starting here, the load is 4, and it stays 4 all the way across, so it's constant. So that means the slope is constant. So you get this. Here's a pretty important point. We go from positive shear to negative shear, so we pass through the axis. So that 0 point is going to be important for us. In fact, it's going to be so important, I'm going to add it to my template down to my moment diagram temporarily. We'll come back and get that in a second. Let's go ahead and make sure this diagram is correct. So starting here at 6 meters in, where our shear is currently negative 8.5, how much does it change over the next meter? Well, change is the area in the load curve. So let's see how much the load curve change is. What's the area in the load curve on the next meter? 0. So no change. Still negative 8.5. And of course, the slope of that curve is given by the load. And we just looked at it. The load is 0, so 0 slope is horizontal line. Now, as we go from left to right and pass underneath this concentrated load, how does my shear change? It's equal to the value of the load, which is 4. Is that positive or negative?
Negative.
Negative. So 8.5, negative 8.5 minus 4a is 12.5. And then the change over the last meter is given by the area in the load curve. And of course, the area in the load curve here is 0, so no change. Yay! We found our way. We made 12.5. And the slope is equal to the load, and the load is 0, so 0 slope, horizontal line, and there's your shear diagram. What's the maximum shear in the beam? Yeah, positive or negative? Positive. All right, now we got a little bit of work to do because we need to come back and find this distance here. There's a couple ways you can do it. These two triangles are similar, so you could do similar triangles. The way I like to do it is I'm going to assume that this is some distance. I'll call it x1. And I'm going to project that back up to my diagram. So really the change in shear from 7 to 0 is what? It would be negative 7.5 kilonewtons, right? If I start at 7.5 and I end at 0, I really need to add a negative 7.5. What's the area under the loading curve under the same spot? What is this area right here?
8.
Well, what's the base of that triangle, rectangle? It's x1. What's the height? 4. So the integral, oops, wrong color, sorry. The integral of my load is going to be negative 4 because it's acting down x1. And those two things are equal. All right? So that gives me an equation of negative 4x1 equal to negative 7.5. If you solve for x1, you get less than 2, 1.875. And that would be meters. So now I'm ready to go. So now I can draw my moment diagram. So let's first establish a positive x-axis, positive moment. All my values will be kilonewton meter. And let's put on there what I know. Do I know the moment anywhere? Yeah, we talked about it earlier. What's the moment at A? 0, so I should start at 0. And whatever I do, I need to come back to the moment at B, and the moment at B is 0. Let me just kind of wall this off so you don't pay attention to it. Now, when we do moment, we want to do the change in moment is going to be the integral under the shear diagram. And of course, the slope of the moment diagram will be equal to the value of the shear. So we're going to use those relationships to turn our shear diagram into a moment diagram. So again, looking over the first meter, there's a unique segment of shear. That little area is a rectangle. It has an area of what? Base, which is 1 meter, times height, which is 15.5. And that's a positive area. So I'm going to have 0 plus 15.5. And I get, what do you know? 15.5. And what's the shape between there? According to my relationship, it's equal to the value of the shear. And the shear everywhere in the first meter is constant and positive. So here's a constant positive slope. Okay? So now the change in moment over the next 1 meter would be this area. I'll kind of double hatch that so you can see it. Just that little part of it. And that little part again is a rectangle, so it's base 1 meter, height of 7.5. So what's 15.5 plus 7.5? 23. And the slope in that case of the moment diagram is given by the shear. And again, the shear is constant and positive, but you'll notice the value is slightly smaller, so the slope is slightly less. So this is a steeper value, a little bit smaller. Now, what's the change in moment from 2 meters to this x1 distance, which we calculated as 1.875? Well, the change in moments are in the shear diagram, and that part of the shear diagram is a triangle. So it's 1/2 base times height. So it'd be 1/2 base, 1.875, times height, 7.5. What's that change? Like 6 or something? 6 point something? 7 point something? What do you guys get? You guys watching Fuzzy Cat videos again, not doing this? What'd you get, Mr. Yang? 7.03. Anybody else get that? Yep. So what's 23 plus 7.03? 30, basically, right? I'll just write 30. And what's the shape of this curve? Well, the shape is given by the slope. So if I start right here, the slope is 7.5 positive, but it decreases to 0. So that means I should have a 0 slope here. And if you kind of fit this, you get a parabola. So that was all the positive areas to get me up here. All these negative areas hopefully will bring me back to 0. So let's try to see what the next bit is. So now the change in moment from this crossing point to here is what? If this is 1.875, then this, I didn't draw it to scale obviously. This other side is going to be 2.125, right? 4 minus this. So now the amount it's going to drop is the area of this triangle, which is 1/2 base 2.125 times height minus 8.5. What's that? Negative 9?
Yep.
Subtract that from 30 and you get 21. Let's see if I can draw this appropriately. And we're going to start with our moment. Slope of the moment diagram is the shear, so we're going to start off with a 0 shear, just like we ended here, and it should get progressively larger. And I'll try to draw that in. I may not get it just right, but you'll get the idea. Now the next change over the next meter, so the change in moment is the area of the shear diagram. What's this shear diagram area? That's easy. It's a rectangle. Has a base of 1 and a height of 8.5. So what's 21 minus 8.5? 12 and a half. This is where my slope's going to get messed up. I'm going to try to draw it as best I can. And the slope connecting these two values should be the shear value, and you can see the shear value is constant and negative. And then the change in moment over the last meter is this part. I'll double hatch that so you can see it. And that area is a rectangle. That's easy. So it has a base of 1 meter and a height of minus 12.5, and you can see 12.5 minus the change, negative 12.5, does bring us to 0. And then the shape of the curve here in between is given by the value of the shear, and the shear is constant and negative. And this is the part I almost got it right. Yeah, it's slightly steeper than the previous section. So where is the maximum moment in this beam? That's the value. Where would it be located? It looks like 1 meter plus 1 meter plus x1. It looks like 3.875 meters from A. So if you would have written this as 1, 2, 3, 4, 5 equations, you would kind of guess that it would be somewhere here in the middle. You'd have to figure out where that equation maxed out. You'd have to plot it and try to figure that out. So this is actually a little better off. We know exactly where it's going to occur. It's going to occur usually associated with the fact that the shear is 0. So there we go. I like this problem too. This is very test-worthy. Any questions about this one?
I have a question.
Yeah.
Are you concerned for drawing the hash marks?
No, I just do that to help you guys see it. I just try to separate the little changes so you can see which part of the curve we're going to be doing. The other thing I'm concerned about when you guys do this are the important values and the general shape. It's possible if you start off drawing this thing and you don't really try to draw it to scale, then you can get over here at the end and these slopes won't be exactly right. We know that the slope in the last segment has to be larger than the other segment, and it may not come out that way in your graph. I don't really care so much about that. What I do care about is the shape. So I do want you to show me that it's linear, or it's quadratic, or it's cubic, but they don't have to perfectly match. Because it's just a rough sketch. All right. We're done with that one.